Hi, everybody. We're about to start now. So for today's edition of the Spectral Geometry in the Cloud seminar, we have the pleasure of having Steve Zelditch from Northwestern University, who will talk to us about eigenfunction restriction problems today. If you have any questions during the talk, you may either unmute yourself or ask them in chat, and we'll relay the questions. Steve, the floor is yours.
Okay, thank you very much for coming. So my talk is about eigenfunctions rather than about eigenvalues, and it has to do with a problems. Let me just have to make this a little smaller here to fit it onto the screen. Hold on. So these are called eigenfunction restriction problems. So we're given a Riemannian manifold, which I will assume to be compact, and I denote the eigenvalues of it by lambda j squared. On the other hand, I take a submanifold, H of dimension little d, inside of my ambient manifold of dimension n, and I restrict the eigenfunction to the submanifold. So there now exist quite a lot of studies of restrictions of eigenfunctions to submanifolds. There are, I will present the motivation in a slide or so, but there are motivations coming from just pure spectral geometry, where you're interested in whether eigenfunctions have special types of concentration properties on certain submanifolds. So when eigenfunctions concentrate, we all know that they tend to concentrate with respect to some invariant measure for the geodesic flow, but we can also study the concentration properties in the physical space on the actual manifold. On the other hand, it's quite possible that the restriction of the eigenfunction is completely zero on some submanifold. For example, if you have a isometric symmetry of it, like a left-right symmetry, and H is the axis of symmetry, then functions which are odd with respect to the involution will vanish. So lots of different things could happen. And we're going to be looking at all possible submanifolds in all possible Riemannian manifolds. So when we study restriction problems, we are really concerned with sequences of eigenfunctions, not really so much individual eigenfunctions. So although this, the most famous type of restriction problems are what are called Fourier restriction problems, which are among the most popular problems in harmonic analysis, these kinds of problems where you restrict eigenfunctions in the physical space are of a different nature, although they actually are related. So what are we interested in? Well, most of this talk, I'm going to assume that my ambient manifold is two-dimensional and my submanifold is a curve, partly because it's easier to write down formulas. And what we do is, so if the submanifold is a circle, it's a closed curve, then we can expand the restriction of the eigenfunction as a Fourier series on the submanifold, and here S represents arc length, and we get certain Fourier coefficients A, N, F, E, K, which are given by the obvious formula, but we're restricting the eigenfunction to the curve, and this really a parameterized curve here. So my talk is about these Fourier coefficients, the Fourier coefficients of the restriction. So this is the first cautionary note, which I will repeat as time goes on, that when people talk about Fourier coefficients of eigenfunctions, very often they don't really quite mean these Fourier coefficients. Rather, the curve H is often a member of a one-parameter family of curves. And in the most standard classical cases, you can separate variables. So if R represents like a distance from H, H could be like a point, or H could be a circle centered at a point, or H could be a closed geodesic or a horocycle. Then oftentimes one can separate variables, and one can express these Fourier coefficients as other coefficients, which I call relative Fourier coefficients, against certain special functions. This is like universally how it's actually done in the theory of automorphic forms. So in automorphic forms, this would be called the Fourier coefficient rather than this. But because there's no real general theory of how that works for general metrics on general manifolds, I'm going to refer to these as the Fourier coefficients. But it should be kept in mind that the kinds of problems I'm going to be discussing, you could, in special cases, you could ask them about these kinds of relative Fourier coefficients or these kinds of absolute Fourier coefficients. All right, so restriction problems have been studied for decades, well, many years. Actually, they go back to the 1920s or even the 1880s if you want to trace them back. And there are two groups of people who study them. The analytic number theorists came first, and they've been studied since the time of Hermite and Jacobi. In fact, the Fourier coefficients of theta functions have meaning in terms of representing numbers in terms of quadratic forms. So it's a classical subject. PDE people have been studying these kinds of restriction problems at least for the last 30 years, I guess. So the types of problems people study are the L2 norms of the restrictions. That's or you can study linear functionals associated restrictions, like these are called periods or averages or just integrals of the restricted eigenfunction against the test function f. Or one can study what's called quantum ergodic restriction theorems, where you integrate the square of the eigenfunction against the test function. In all these problems, the issue is to look at behavior along subsequences to understand estimates or asymptotics. In this talk, we're studying Fourier coefficients of the restrictions. So it's more similar to averages than any of these other things. So here are some references to the literature. LP norms of restrictions were studied systematically in a paper of Burke and Girard and Svetkov, which later on there are many papers of this type by Hu, Bruggemann, Hazari, Riviere, Blair and Saugcastle, Tacey, Reznikov. I'm undoubtedly missing names. And the interest there is to try to characterize how the size of the Fourier of these L2 norms, well, it should depend. It depends on the metric. It depends on the sequence of eigenfunctions. It depends on the submanifold. In particular, it depends on whether the submanifold has a non-degenerate second fundamental form or a degenerate one. So the degenerate one, where the submanifold is totally geodesic, is a kind of extreme case. So John Toth, for example, studied these kinds of problems where the Laplace operator is quantum completely integrable, and then you want to study for which type of submanifolds you have sequence of eigenfunctions which concentrate maximally. And with Toth, we studied that kind of problem in shrinking tubes around geodesics and other submanifolds. Mike Geis has recently studied a kind of empirical measure of L2 norms of restrictions. So as far as L2 norms go, of course, the L2 norm is the sum of the squares of these Fourier coefficients. And consequently, when we study the Fourier coefficients, we are refining the study of restricted L2 norms. And we're trying to understand which of the Fourier coefficients is causing the L2 norm to be large. For example, in cases where the L2 norm is maximal on some submanifold, how do the AN of phi j's distribute among the n's? So this is a new type of problem which is related to what Wiener used to call a spectral problem, which is that we look at the Fourier coefficients of the eigenfunction, and we're trying to understand which ones of these Fourier coefficients is causing the L2 norm to be large. So we study what's called the Fourier profile, which is the map from n, the Fourier coefficient, into the mod squared of the n is just an eigenvalue of a circle, and then we look at the mod squared of the Fourier coefficient, and we view it as a function of the ratio of n over lambda j, where lambda j squared is the eigenvalue. So it's a sort of frequency along the curve versus the frequency on the entire manifold. So the profile is essentially equal to 0 outside of -1 to 1 when n over lambda j is outside of -1 to 1, because n is like an angular momentum and lambda j is like an energy, and the angular momentum is less than the energy. So we normally study this when this ratio is between -1 to 1. And we really study it as a function of n over lambda j. And we can formalize the question by making this empirical measure. So at each one of these n over lambda j, so lambda j here should be fixed. I'm sorry, the left-hand side, that k should be a j. And so for each j, so for each eigenfunction, we define a measure on -1 to 1 by at the point n over, it's supported at the points n divided by lambda j, and at those points we put the mod squared of the Fourier coefficient. And we are interested in the asymptotics of this measure as j goes to infinity, as the eigenvalue of the eigenfunction goes to infinity. So there are all different types of things that can happen here. On the one hand, and we'll see in a moment, there can exist exactly one Fourier coefficient, for which this is non-zero. And on the other hand, the Fourier coefficients might be kind of uniformly distributed in the among these different Fourier modes. In other words, the AN of phi j squareds could be essentially constant. This problem that I'm mentioning is not far from science fiction to people who are experts in spectral asymptotics. You know, this is a kind of problem that I would suggest that physicists might be interested, like Uzi might be interested in it. And indeed, people and physicists study these problems since at least the 80s. And so I don't think I will have time to really mention it, but one of the first of these kinds of problems, of these kinds of empirical measure problems to be studied, was the case where you take a hyperbolic surface and your curves are circles centered at a point. In fact, you lift the eigenfunction from a compact hyperbolic surface and you lift it to the universal cover hyperbolic disk, and you look at it in concentric circles, and you get there you really seriously get the difference between absolute and relative Fourier coefficients, because you get a Fourier expansion in terms of, this is due to Helgeson, in terms of generalized spherical functions, and you want to eliminate the role of the generalized spherical functions to get coefficients an. And Auric and Steiner kind of graphed this kind of Fourier profile. This was my entree into the subject in some sense. They graphed the Fourier profile and came up with the hypothesis that really, it's, as I say in this cautionary note, they really studied the capital ANs because these GNs would be spherical functions and they're kind of irrelevant. Everybody understands them, they're not interesting. And they found that these ANs, in some sense, behave like IID normal random variables. So that's the kind of way out there, but motivating type of problem that gives rise to the subject. So one expects that, you know, to really study this problem at the moment, you probably would need to study it on a computer numerically, the way that Auric and Steiner did. But in any case, we're interested in getting as close to this problem as we can. So there are cases where, like in quantum integrable cases, you would expect that eigenfunctions have basically one series Fourier mode. On the other hand, in the quantum chaotic case, you would sort of expect that these Fourier modes should be, roughly speaking, constant in the possible interval where n over lambda j is between -1 to 1. But again, with that cautionary note that that may apply to the capital ANs and not to these little ANs. So so that gives you some idea of like what we're heading for. What would be kind of a very long-term problem here. So let's review a little bit the history, like why people get interested in this. So Fourier coefficients of automorphic forms, these are a classical topic. Every book or article on automorphic forms will have a section on the Fourier coefficients. So by an automorphic form, I just mean an eigenfunction for like a hyperbolic compact surface or any hyperbolic surface. So you take the upper half plane, divide by a discrete subgroup, usually co-compact or finite volume. And the reason people did that is that ever since 1880s, people realized that the Fourier coefficients contain very important information. Now, the earliest ones, which are due to people like Hermite, have to do with Fourier coefficients on closed horocycles for the upper half plane mod SL2Z. So you have a one parameter family of closed horocycles, and you can study the Fourier coefficients on these horocycles. And this is almost always the starting point of any paper about cusp forms for SL2Z. And so Hecke, there's a long story there. Hecke and Peterson related these Fourier coefficients to things called eigenvalues of Hecke operators. Maass in the 40s generalized what they were doing to see infinity eigenfunctions rather than holomorphic ones, eigenfunctions of the Laplacian. So Maass might be said to be the founder of the exact kind of problem that we're studying. And then it was studied by Selberg and Roelcke, Rankin. So then, in some sense, the origin of the analytic study that in the generality we're talking about is due to Bruggemann and Kuznecov. And all of the techniques really since that time, or many of them, really come out of the works or adaptations or generalizations of what Bruggemann and Kuznecov did. Personally, I've never read the papers of Bruggemann and Kuznecov because both are in languages I don't speak and they're not translated. But and then shortly after Bruggemann and Kuznecov, well, Helgesen, as I mentioned, studied the Fourier coefficients at infinity, so to speak, with respect to the ideal boundary. Then Hejhal and Good did a kind of more analytical study of Bruggemann and Kuznecov. This was all taking place in the 70s. My own entree into the subject came because I was a postdoc at Columbia, and Hecke was studying these Kuznecov, what they call relative trace formulas in the Langlands program. And I knew the theory of Deutschmann-Gilliman about how to generalize the Selberg trace formula. So I generalized the Kuznecov and Bruggemann formula in the mid-80s. So more recently, Scott Wolpert had a series of papers where he studied these Fourier coefficients, and probably the best estimates on Fourier coefficients in arithmetic cases where you have Hecke operators is by Simon Marshall in the 2010s, I guess. So, all right, so the reason really why Bruggemann, Kuznecov, Hecke, Langlands, all these people were interested in relative trace formulae is that Selberg's formula is, of course, giving you direct relations between eigenvalues of Laplacian and conjugacy classes of the fundamental group, but it's quite complicated if you have finite volume but non-compact manifolds due to the role of Eisenstein series. But they realized that rather than integrating over the diagonal in the manifold across the diagonal, which is non-compact and leads to multiple problems, if you integrate over a closed horocycle, closed geodesic, or a circle, it's all compact, and actually there's no analytical problems anymore. So this was sort of their original motivation, and it turned out as well that for the right choice of curves, you could estimate your write-down formulas for Fourier coefficients in terms of interesting quantities. So this was a classical thing in number theory. They just generalized it to C infinity Maass forms. All right, so in semi-classical analysis, as I mentioned, in the 80s, I did unto Kuznecov what Deutschmark Gilliman did unto Selberg. I just generalized it in the kind of obvious way using Fourier integral operator theory, and got a general estimate that if you have a hypersurface in any Riemannian manifold, then the periods, just the integral of the restricted eigenfunction over the submanifold was bounded. So that's for a hypersurface, and for any submanifold, you get a bound on these periods. So these are often called periods of automorphic forms rather than Fourier coefficients. So this is like taking a zeroth Fourier coefficient, because f is a fixed function that does not depend on the eigenvalue of Pj. And this, there are quite a lot of papers about this, maybe 60 or 70 articles over the last 5 to 10 years, improving this result, because this is a generic result. This is a result for just any M and any H. But if you start making assumptions, H has positive second fundamental form, H is totally geodesic, M has negative curvature, all these different types of assumptions, you can get special types of estimates on what is going on. And the purpose is to try to determine which types of metrics, which types of submanifolds saturate these kinds of estimates, and for which ones you can improve them. So there are quite a lot through the SOG, Wyman, Shi, Song, Kanzani, Gelkowski, Toth, Kanzani, Gelkowski. So there's quite a lot of these. All right, now in the chaotic case, for sure the chaotic case is the one that people are most interested in, but they never saturate any of the estimates. And so, they're very complicated, of course, but so Toth and I in 2013 proved what's called the quantum ergotic restriction theorem, which means that if you restrict a subsequence density 1 subsequence of eigenfunctions to anything that we call asymmetric submanifold, that's like a manifold where it's like not the case where it's the fixed point set of an isometric involution, because then half the eigenfunctions vanish. So it's asymmetric rather than being symmetric. So there's a generic condition, and so for generic hypersurface, so this should be a hypersurface, the eigenfunction squares tend to 1 along the hypersurface. If you restrict the eigenfunctions to the hypersurface, then they tend weakly to 1. They're quantum ergodic along the hypersurface. So so if we make f equal to 1, it says that the L2 norms of these restrictions are basically equal to 1. So we find out that the sum of the squares of the Fourier coefficients are basically equal to 1. If we had, so here, this is the square root of the eigenvalue. So we have roughly lambda j, but we have lambda j Fourier coefficients here. Since we're squaring the Fourier coefficient and we sum them up and we get 1, that means that the typical Fourier coefficient is of size lambda j to the minus 1/2. And it's a I guess any physicist would conjecture that there should be no exceptional eigenfunctions, no exceptional Fourier coefficients. they should all be pretty much the same. So you would sort of guess that these particular Fourier coefficients should all come out to be lambda j to the minus 1/2. And by Chebyshev's inequality, which Jung and I used in a nodal domain problem, that's true for the typical Fourier coefficient, but not necessarily true for them all. And that's kind of a main obstruction in a lot of these papers, that we have no control over every single Fourier coefficient. We only have control over typical Fourier coefficients. So as far as like results on every single Fourier coefficient goes, the best results I know of to date, which only apply to Hecke eigenfunctions or Simon Marshall, and if I understand his notation correctly, away from the edge, that's where the n is equal to lambda j. So away from the edge, the Fourier coefficients are at most size lambda to the minus 1/18. So that's a good result. And this one is sort of reflects the fact that it's using L function methods, arithmetic methods, because if you use microlocal analysis, I don't think you can improve on something like 1/log lambda. In fact, such results have not even been proved, although one expects that they can be. But yeah, so at the edge, something unusual happens, and that's perhaps the most interesting Fourier coefficient in general. When the n is basically the same as lambda j, then you can get an enhancement on the size of the Fourier coefficient. And why that happens is, of course, one of the motivations in the subject. Why do you get, or in fact, do you get enhancements of the Fourier coefficients at the edge? And again, this this warning I mentioned should be very appropriate. Since if you can write the Fourier coefficient as an absolute Fourier coefficient, as a relative Fourier coefficient times some kind of special function, the problem is that special function may be enhanced at the edge, whereas the relative Fourier coefficient might not be. So that's another kind of interesting question in this subject, and that's exactly what one expects based on the numerics of Aurich and Steiner. The relative Fourier coefficients are not enhanced at the edge, but it's really the fact that they're relative to a special function, and that thing is enhanced at the edge. So all of these things are really quite open problems that have not been studied very much. So now I'm going to state the rigorous results. And so let me do this in a general context of having a submanifold of a compact Riemannian manifold, and we look at the eigenfunctions of the submanifold. So that generalizes e to the INX if we had made the submanifold a circle on a surface. And we just restrict the eigenfunction and expand it in terms of the eigenfunctions of the submanifold. And our question is, how are these Fourier coefficients distributed? And I should mention that when I say Fourier coefficient, we can put in a test function inside of the inner product of the restriction of phi j and the ambient and the restricted eigenfunction as well, with no change in anything. I don't want to go too fast, but are there any remarks or comments, questions? Okay, so let's look at some really simple examples. When we want to study examples, naturally we look at quantum integrable systems. We look at flat tori, we look at round spheres. Victor Gilliman looked at totally geodesic flats and higher rank symmetric spaces and proved a very nice theorem about them in the late 70s. Simon Marshall kind of picked that up and studied the totally geodesic flats and locally symmetric manifolds. So we can look at a bunch of specific examples where we can try to understand what is going on. So here's a question for spectral geometers. So in some cases, the only ones I know are when you can separate variables. it happens that when you restrict the eigenfunction of the big manifold onto the submanifold, it actually restricts to an eigenfunction of the submanifold. So this is certainly what happens on a flat torus. If you restrict the plane wave on the big manifold, on the two-dimensional torus, and you restrict it to a coordinate circle, a circle being a subtorus, it's a geodesic, then it just becomes a an exponential on the geodesic. So if you did it on a unit disk, then as you all know, you separate variables and you get e to the ik theta times a Bessel factor. And if you restricted it to the boundary, for example, or any concentric circle around the origin, you just get e to the ik theta. So you get eigenfunctions on the circle, but you're multiplied by a special value of a Bessel function. And that's again what I mean by this relative versus absolute business. If you measure the equipartition of the Fourier coefficients, you don't, it's your choice whether to include the Bessel factor or not. So another example is, I should have put this in, I'll do it in another slide anyway. But of course, you can play the same game on a round sphere. You can take the standard basis YLN, and you can restrict this to YLN means joint eigenfunctions of the Laplacian and a rotation around the third axis. And so when you look at the orbits of rotation around the third axis, you get latitude circles or you get the equator. Well, you could restrict these eigenfunctions, and I should have said that, to these latitude circles or to the equator, and they will have exactly one Fourier mode. Okay, so these are examples where the Fourier profile along the equator would be like zero everywhere except at one point, and then it jumps up at one point. And it makes quite a big difference whether you restrict them to latitude circles or to the equator. As we'll see later on, they're smaller on the latitude circles. They're bigger on the equator. The equator is totally geodesic. The latitude circles have non-degenerate second fundamental form. Okay, another thing we could do is to take these exact same YLNs, but restrict them to a meridian instead of to the equator. So this is not, the meridian is orthogonal to the curves that are the rotational curves. Like we could take a zonal spherical harmonic, and then we could restrict for the rotations around the third axis, and then restrict it to a meridian curve. And then it has Fourier modes of all types. None of its Fourier modes are zero. So its Fourier profile it's no longer just sticking up at one point. It's fairly uniform. In fact, there are explicit formulas for the Fourier coefficients in classical, like Szego figured out the Fourier coefficients of these. You can write them down in terms of Legendre functions. They're not easy to figure out. So it turns out that in the range of n between minus capital N and big N, they go between 1 over little n and 1. So they're different depending on which Fourier mode. The profile is not a constant profile, but it's fairly uniform. So here's a question for spectral geometers. All these examples, like when we take a zonal sphere, when we take a YLN, or we take eigenfunction of a disk and we restrict it to a circle, a latitude circle, or an equator, they become eigenfunctions of the submanifold. To my knowledge, it's not known, like exactly when restrictions of eigenfunctions of the big manifold are eigenfunctions of the submanifold. And you can pose that problem in the strong form by assuming all of the eigenfunctions have that property. You could do it just like some eigenfunctions have that property. You have your choice. But in any case, it's not known. So let's take
my guess, if you want an example, that my guess, if you take your favorite flat torus and restrict to a curve which is really curved, then you never get
Right.
an eigenfunction.
I believe you. I believe you. I just was saying it's you know, it's kind of like a general problem, like when you can do it. All the cases I know, you can separate variables, and perhaps that's the answer to the question, that you can only get these restrictions to be eigenfunctions in cases where you can separate variables. But of course, that's sort of
It
a
will
local
depend
versus
on
global problem.
H. It will depend on H. So the
Yeah,
example
it
you showed
absolutely
was when H was a flat closed geodesic, and then
Yeah.
you can restrict. But
Yeah.
when H, in this particular example, if H is a curve, then I
Right.
think I know how to show that it's never an eigenfunction.
That's right. That's right. And you know, it's like generally what you mean is that you look at, like, if you have a hypersurface or a curve on a surface, you look at you look at a collection of curves where you fix the distance to your H. So these are like Fermi normal coordinate level sets. So for example, if you have a closed geodesic and you were on a torus, you'd just be looking at closed geodesics where you kind of just rotate it away from H. If you had a distance circle, then you'd be looking at concentric circles. And when I talk about the fact that you could separate variables, I guess you mean with respect to those. But I guess on a flat torus, you could separate variables with respect to a distance circle, and you don't get eigenfunctions on the distance circle. So it sort of depends. But okay, so these are sort of like the most famous examples. So let me mention them, because like anybody who's worked in this field, immediately they would look at Gaussian beams. So Gaussian beams correspond to closed geodesics, and a Gaussian beam oscillates at level e to the INS along the geodesic in arc length s, and then in the transversal direction to the geodesic, it's Gaussian decay. So it's like a laser beam around the geodesic. So this is in some sense another motivating example. When people study the periods of eigenfunctions, they restrict them to the submanifold, and then they integrate it. Well, these Gaussian beams are absolutely explode along their geodesic. They saturate the L2 norm bounds. But on the other hand, their periods are zero because e to the INS is orthogonal to the constant function 1. So what's wrong? What's wrong? Well, obviously, we should be looking at Fourier coefficients, and we shouldn't just be looking at periods. That's sort of absurd. Why are we only looking at periods of things? That's a zeroth Fourier coefficient. If I integrate my Gaussian beam against e to the minus INS, then I get actually the square root of the L2 norm, because there is only one mode that's not zero. So this is sort of the type of example that motivates studying the Fourier coefficients, because for the Gaussian beam, its L2 norm saturates the general L2 norm restriction bounds. In fact, it's kind of the unique object that does. I won't say that very seriously, just as a kind of intuition. And yet it has only one Fourier coefficient that's not zero. And consequently, it also is going to saturate Fourier coefficient bounds. So Gaussian beams just permeate the theory of eigenfunctions. So, so we also notice that the Gaussian beam is a special case of YMNs, where m is equal to n. It's an edge case. So Gaussian beams represents what we call the C=1 edge case of Fourier coefficients. The Fourier coefficients right at the edge of the possible non-trivial Fourier coefficients, and right at the edge, it just booms. So, okay, so if you took any one of these YMNs, as I mentioned, they have only one non-zero Fourier coefficient along the equator. The size of the Fourier coefficient depends on m. Here I'm making gamma closed geodesic the equator. As Mike Geis has been studying, if you make H a latitude circle instead of a closed geodesic, then some of the YMNs, they can also kind of explode. when m over n is well related to the latitude circle. Then YM has a big fold singularity and explodes, but not as much by any means as the Gaussian beam explodes at the edge of the interval. So the explosion at the edge of the interval, when gamma is a closed geodesic, it never happens if it's a latitude circle. If it's a closed geodesic, you have eigenfunctions which have enormous Fourier coefficients. You do not if it's a latitude circle, for example. So that raises another question of like, when exactly do the Fourier coefficients explode? So just to review it, we have Fourier coefficients, we make empirical measure, and we graph n against a n of k. And we've seen examples where the Fourier profile is almost constant. That's like a zonal spherical harmonic around a meridian. We've seen examples where it's like completely like zero until it hits the edge and then it blows up. It can blow up in the middle if you take a YMN and restrict it to a latitude circle. So we see that there are quite a lot of phenomenon going on here. Now I'm going to state the rigorous results on the subject. So the rigorous results on the subject are something that's been studied by Yakun Shi, Emmett Wyman, and myself for the last few months. And what we do is, instead of looking at the empirical measure, we integrate it over some interval. So when you write it out, it means I should not be summing over lambda j here. Sorry, this is just one fixed lambda j. So forget about that. That's not there. So skip this sum here. It's just the inner sum. You sum over eigenvalues of H, and you look where the eigenvalues of H are roughly some constant C times the ambient frequency. And so these are very narrow windows. We're not able to study a single Fourier coefficient. We can study Fourier coefficients centered in small windows around the value C times lambda j, where lambda j is the ambient frequency and C is between 0 and 1, or just less than or equal to 1. So this is the best we can do in terms of focusing in on a single Fourier mode. This is definitely focusing on one eigenfunction, but we're only able to do some kind of sum over the Fourier modes. And so we break them up into the windows defined by this number C. C is going to play an important geometrical role in everything. So C, for example, could be 1, and then we're at the edge. It means that we're within, the mu k is within epsilon of lambda j itself, so it's in an epsilon interval around the edge of the interval. To make this a function of mu k divided by lambda j, well, just divide by lambda j, and it says mu k divided by lambda j minus c is less than epsilon over lambda j. So this is what in semiclassical analysis would be called an H-bar window, a semiclassical H-bar window around mu k over lambda j. And the C here is very familiar in semiclassical analysis and represents a kind of energy. We're sort of asking that mu k over lambda j be very close to C, semi-classically close to this value C. So that's a very standard thing to do when studying a single Hamiltonian, and you want to study eigenvalues near an energy level. So here C represents kind of like the energy level. So these are called sharp sums. It would be somewhat easier. These are jumps. I should not have done this double sum here. Here's where I do it. These are what we call Kuznecov-Weil sums. So here we sum over the eigenvalue lambda j. Not only is it very difficult to study one for a coefficient of one eigenfunction, it's actually difficult to study a window of Fourier coefficients for one eigenfunction. Generally, we start by averaging over the ambient eigenvalue lambda j, and that's what gives us Kuznecov-Weil sums. These are the kinds of things that in spectral asymptotics we're able to study. And then once we understand how that behaves, we start studying the jumps of this Kuznecov-Weil sum at the eigenvalues. That's what J is supposed to be. That's why I don't want this additional sum here. So when I state the results, keep in mind that the most interesting problems have to do with the jumps. That's like a second term. I'm only going to be really presenting results here about first term and estimates on jumps. So there's quite a long way to go if you really want to understand empirical measures. So here's like the first result of Emmett, Wyman, Yakun Shi, and myself, that we look at general manifolds of dimension n, general submanifolds of dimension d, and we stay away from the edge. We fix a number c between 0 and 1. We fix it to be greater than 0 because I did that already, and many other people have studied that. But we make it less than 1, which means we're staying away from the edge. Moreover, we're not making any assumptions whatsoever on the metric and no assumptions on the submanifold. I don't really want to explain this assumption here because we don't really need it. It's just that it's more technical to state the result without it. And we find that the Kuznecov Weyl sums are universal. They don't care about the metric. They don't care what kind of submanifold you have. You always get a certain coefficient, and it's times lambda to the n minus 1. So a weird thing about this is that it's actually not weird once you understand what's going on, but a weird thing about this a priori is that the power of lambda here does not depend on the codimension of H. It's the same whether H is one-dimensional or n minus one-dimensional. It's 1 degree lower than a Weyl sum would be. That would be lambda to the n. So this is 1 dimension lower, and there's a very nice reason why that is true. And the leading coefficient depends on C. This thing does not depend on D, does not depend on C, but the leading coefficient does. So all of these details are rather interesting, but it depends on D. You take this number C and you raise it to the power D minus 1 minus C squared to the codimension power times the Hausdorff dimension of H, Hausdorff volume of H. So you notice that, this one here is going to be very small at C equals 0, unless D equals 1. This one over here, n is always bigger than D. D is never more than n minus 1, more than n minus 1. But different things could happen here. This coefficient could blow up when C equals 1 in the hypersurface case. But other than the hypersurface case, this exponent here is positive. So when C equals 1, it actually goes down. So it's kind of curious why this effect is that we sort of saw in the case of a round sphere and the equator that we had explosion when C equals 1. But that's because we chose D equal to 1, n equals 2. That's the hypersurface case. And then this coefficient explodes. By studying these things, we get a jump estimate. And so the jump estimate, here we sum over all the different eigenvalues equal to lambda j if there's multiplicity. In general, there's no sum here. This is just 1. And we're just summing over the inner one. This outer sum only occurs when we have multiplicity. So in this case, we're getting some estimate on the sums of squares of Fourier coefficients lying in a semiclassical H-bar window around C times lambda j for every C. And so we get this type of estimate over here. So these estimates are sharp. All these estimates are actually, this remainder estimate or jump estimate is achieved on spheres. And so, of course, the question arises, when are these jumps really so huge? Why are they achieved on spheres? First of all, you have a big multiplicity of eigenvalues on spheres. So this is a large sum here. Then when you do these inner sum estimates, these are eigenvalues of subspheres. Subspheres also have huge multiplicities, so this is also a large sum. But I warned that these are not really exactly the reasons why this thing is saturated on a round sphere. So these are subsaturated on closed geodesics in general spheres or subspheres of general spheres. So let me explain what is the geometry that is underlying this. So back in the old in the days when you study averages or periods, everybody discovered that the geodesics which are contributing are the ones which are orthogonal to H at both endpoints. So these are important geodesics in geodesic geometry anyway. The geodesics are orthogonal to H at both endpoints. Well, what would you expect if you didn't take the 0th Fourier coefficient, but you took a coefficient which was between, the Fourier coefficient n is almost like c times lambda, where lambda is a big number. Then instead of getting geodesics which are orthogonal to H, they start tilting, and you get geodesics which make a certain angle with respect to H. And that's what this number c, it's not exactly the angle or cosine of the angle, but it's sort of like the cosine of the angle. So the c here represents that the geodesics are now making an angle with respect to H. They're not tangent to it. That would be c equals 1, you're tangent to H. When c equals 0, you're normal to H. And if c is between 0 and 1, the geodesics which contribute to this problem, the asymptotics, are making an angle like cosine of the angle is c with respect to H. And the number, it's more than that, actually. It's more complicated. So something new happens when c is greater than 0, which is that you don't just get geodesics of the big manifold M, which make an angle with respect to the submanifold. What you get also is that you have what we call biangles, which is that you have geodesics of that kind in M, but they're connected by a geodesic of the submanifold. So there are two different geodesics, one on the submanifold, one on the big manifold. So we call it a biangle because it has two geodesic sides. And there's a relation between the length of the geodesic on M and the geodesic on H in order for it to contribute for a particular value of C. So, okay, so these are we call CST biangles. And one can say that the governing equation for this problem is not like, so as we know from Deutschmark-Gilliman, periodic geodesics play the big role. As we know from averages, normal geodesics play the big role to H. Here, these CST biangles play the big role. So the governing equation is this geodesic equation here. In the geodesic, so C equals 1 is the edge case. And to my mind, it's the most interesting case. And you have to break it up. It's radically different accordingly as H is totally geodesic or H is second non-degenerate second fundamental form. And this defining equation becomes trivial. It becomes almost trivial when C equals 1 and H is totally geodesic. The S's all kind of cancel out. The covectors have to be tangent to H. And all you do for a biangle is you go out S units and you come back S units along a geodesic of H. That's when T equals 0. And for general T, you go out T plus S units and you come back to S units. And in order to be a biangle, this has to close up. And so the S's cancel out. And so T has to be a period of the flow along H. So that's the kind of geometry which occurs. And so this is a new result that when C is equal to 1 and H is totally geodesic, you get a completely different type of asymptotics than when C is less than 1, illustrating why everything kind of changes at the edge. So when, again, with the same notation, N is the dimension of H, D is the dimension of H, now the leading coefficient is N plus D over 2. And so it's very different. And in addition, the coefficient is of a completely different nature. than when c is less than 1. Instead of only involving the test function psi hat at 0, it involves its integral against this particular distribution. I'm sort of running out of time, so I don't really have the time to go too much into this. But this is c equals 1. And in my next slide, I want to compare c equals 1 and c less than 1. See, sometimes when c was less than 1, we got an n minus 1 here. And it's possible, we have to compare those. Oh, I should say that you get also these jumps. The jumps are always 1 lower than the top term. And these are saturated, again, by totally geodesic subspheres of spheres. And they also point out why we got a different answer for Gaussian beams along the equator than we ever would for any other eigenfunction along a latitude circle. So let's make a comparison. So we got this one over here is just basically the Hausdorff measure of h times psi hat of 0, lambda n minus 1. Whoops, pardon me. No, that's right. Here's the formula for the leading coefficient. And that's completely different from this coefficient over here. It's obviously a completely different nature. So it's easy to see that actually when c tends to 1, this coefficient actually does, in some sense, tend. It does, in fact, enforce the behavior when c equals 1. If you let c be 1 minus epsilon over lambda, then this coefficient times lambda to the n minus 1 will tend to lambda to the n plus d over 2. And so when h is a hypersurface, then actually the coefficient you get when c equals 1 is bigger than the coefficient here when it's by 1/2 unit. Just like Gaussian beam along the equator is bigger than what would happen if you had c less than 1. Otherwise, the ones when c equals to 1 are less than or equal to the ones when c is less than 1. So you get no enhancement at all if the codimension of h is bigger than 1. There'll be no enhancement at c equals 1. In fact, you get damping if if the codimension is at least 2. So I'm just going to end with the role of Gaussian beams. Gaussian beams are very rare creatures. They don't occur on every manifold. But when they occur, you can understand what exactly is going on. Because let's just take in a simple example where you take a totally geodesic subsphere of a round sphere. If you take a Gaussian beam of the big round sphere and you restrict it to the totally geodesic subsphere, it is a Gaussian beam of the totally geodesic. Well, if the geodesic for which it's a Gaussian beam lies on the subsphere, then it is a Gaussian beam of the subsphere. If the geodesic of your Gaussian beam on the big sphere is not tangent to the subsphere, if it's transversal to it, then it's negligible. So it turns out that all these numerics can be understood in terms of restricting, in the case of totally geodesic subspheres, the spheres at least, you can understand them in terms of restricting Gaussian beams on a big round sphere to a totally geodesic subsphere. All the numerics can be understood that way. So I guess I better stop here. Thank you.
Thank you, Steve, for the nice talk. We have time for questions. So if you have questions, either write them in the chat or just unmute yourself and go ahead.
Steve, and if we look at Hecke eigenfunctions in the sphere,
yeah, the Hecke eigenfunctions on the sphere, I would expect equipartition of their Fourier coefficients. This is basically what Auric and Steiner were saying. If you have a totally random function, then the Fourier coefficients are going to inherit that randomness. Like you restrict it to a nice thing like an equator or something like that, or you'll get total random Fourier coefficients as you would expect.
Okay.
So I expect equipartition of Fourier coefficients in that case.
I have a very naive question myself. Could you replace the Laplacian by Schrödinger operator with the potential and have some effect of the potential in these cases?
Well, that's sort of like, there are two ways to answer that question. Because when people talk about Schrödinger operators, there are two types. Semiclassical people put an h bar squared in front of the Laplacian, then add the potential. And then the potential is every bit as important as h bar squared Laplacian. They're the same order. Then the governing flow is the Hamiltonian flow for c squared plus v of x. And that's a good question. In that case, you know, all the geometry is gonna change. You're not gonna have geodesics anymore. You're gonna have Hamiltonian orbits, and so they're going to change. And my guess is that everything depends on the energy level, because now, you know, you make EJ of H, you know, make eigenvalues depending on H bar. Every single energy surface is different from every other energy surface. You have a different Fourier coefficient problem for every energy surface. So you have like, you have twice the complexity of whatever's going on here. So that's a very, very nice question. I mean, you know, I would say if you can work that out for harmonic oscillators at first and just find out what happens, harmonic oscillators of Gaussian beams, you can do all of these things for, like, harmonic oscillators are virtually homogeneous, and what goes on doesn't really depend on the energy. But you know, all these problems have like analogs. If you don't put H bar in, then I would say the potential is not important.
So there are two questions in the chat. The first one is by Peter Humphreys. He's asking if anything is known for random spherical harmonics.
About the Fourier coefficient? No, I would, to my knowledge, the Fourier coefficient problems I'm discussing have never been studied by semi-classical or by our group of people until these papers by Wyman, she and myself. There are many, many papers in automorphic forms literature on them, but they don't tend to look at random objects. You know, they don't tend to look at it the same way we do. They use L function techniques and things like that. Thanks.
There's also a question by Amir Vig, who's asking, is there anything that can be said about sub-principal term in asymptotics?
Well, I mean, put it this way. That's a very complicated question to answer, because we're doing a double average. We're averaging in the lambda j, and then we're averaging in the eigenvalues of the submanifold. And this is a very complicated question, because you have like two different test functions when you start studying this, the one involving lambda j's and one involving mu k's, the eigenvalues of the submanifold. So the sub-principal term, you have to really tell me what problem you're discussing. And we've had lots of troubles with this. So let me try to explain this. To somebody working in regular old spectral asymptotics, where you don't have an inner sum and an outer sum, you would probably just look at it in lambda j and want a sub-principal term. This is what I'm sort of calling the jump terms. But the jump terms depend on whether you sum over the inner eigenvalues using a smooth test function, or whether you look at an interval. So one of the things that Wyman and I spent a lot of time studying is this weird effect that if you make the interval of, you look at an interval of lambda j's, and you then look at an interval of mu k's. So you say mu k minus c lambda j is less or equal to epsilon. It turns out that as you vary epsilon, all sorts of weird things can happen. Like on a round sphere, you look at the subsphere, the set of pairs, mu k and lambda j, which differ by epsilon, there are special values of epsilon, which are like 1 over n, multiples of 1 over n, where you all of a sudden get a new string of pairs. Lambda j here would be a capital N, and mu k would be like a capital M, both integers. There would be a new string of things where the integer m differs from the integer n, or c times n, by an epsilon. You get these jumps in the jumps. as epsilon varies, the jumps themselves jump. So to me, the jumps are the most interesting things because we're interested in individual eigenfunctions to the extent that we can handle them, and the jumps are the individual ones. So these jumps also jump. And so when you talk about this sort of sub-principal term, to me, this would really be the interesting thing would be the jumps and the jump. So it's a pretty complicated problem, what we even mean by the sub-principal term. It's not really a well-defined thing. If I put in a smooth test function psi for the mu k's, then it's sort of like the sub-principal term over here. And you don't expect it in general to be able to get any kind of good formula for that. Only in like quantum completely integral cases can you even hope for a formula like that.
Thank you. Does anyone else wants to ask a question or comment? Seems not. So let's thank the speaker again. Thank you very much, Steve. We will return next week with a talk by Derek Kielty, who will speak about degeneration of spectral gap with negative Robin parameter. So everybody have a great week and see you all next week. Thanks again, Steve.
Bye-bye.